Now let's talk about the different type of filters that we will basically learn how to synthesize. So overall, there are roughly 4, broadly speaking, types of filters. So they're all listed here as low pass, high pass, band pass, and band stop. It doesn't mean that we don't need more complicated transfer functions, but it usually means we can synthesize more complicated ones by essentially considering this type of filtering response. I also want to show you here the symbols of that. For example, for low pass, you can see that I'm crossing the 2 bands, while for a band stop, I'm crossing the middle band. So you will often see this in textbooks and papers. This is the typical amplitude response we will consider. So again, notice how the ideal passband response looks like, while the ideal bandstop response looks like. You probably have also already learned from undergraduate courses that none of the 4 responses you see here is actually realizable. So there are certain reasons for that. Essentially, you violate causality issues if you try to realize something like this. So clearly, we have to make approximations for reaching these waveforms. And so the critical question is often, what type of an approximation can we use? So let me remind you of a few approximations that I know you've seen before, and what are the pros and cons of them. So the Butterworth or maximal flat approximation is very useful when your main goal is to basically make as flat of a response as possible. No ripples, just as flat as possible. Essentially, all your reflection zeros here are placed at your center frequency. And as a result of this, your filter has relatively poor selectivity compared to what it could have had if you chose a different approximation. On the other hand, it has, I would say, a medium quality group delay. It's not too bad, it's not perfect, but sometimes it's decent. Chebyshev is slightly more aggressive. Essentially, you buy much more selectivity by allowing for a ripple in here. So if you were to take a zoomed version of that, you will basically find that your passband has a clear ripple, and this comes from the Chebyshev polynomials that we are engaging. So your selectivity becomes much better based on this, but the penalty is that your group delay is becoming worse. So I like to call this not so good. That means that if you're designing a filter where you're specifying group delay, it's not easy to satisfy with Chebyshev. If you don't care about group delay, then Chebyshev is okay. There's another type of filter which I want to spend a little bit of more time, and that's the elliptic type of filter. So the elliptic filter, instead of placing all of the transmission zeros at infinity, which is, by the way, the case for the Chebyshev as well as the Butterworth, all of the transmission zeros are basically here at infinity, and of course at 0 as well. In the elliptic case, we have finite transmission zeros. These are essentially frequencies where S21 is identically equal to 0. This is what we'll specify as a transmission zero. So by breaking essentially transmission zeros from infinity back to a finite set of frequencies, what we're basically achieving is a far steeper curve close to the passband. And that's useful, particularly when you try to reject signals close to your passband characteristics. On the other hand, now the penalty for doing that is that you do have a ripple in the stop band. And so essentially, in these cases, what we normally do is we specify a maximum amount of attenuation that we can, a minimum rather level of attenuation we can tolerate. And then the second part is that, unfortunately, now our group delay, again, is what I like to call not so good. So the elliptic filters have, again, ripple, pretty much like the Chebyshevs do, but they have ripple both in the passband as well as in the stop band. You do have the benefit of killing interferers if you like them too, because they have these transmission zeros, but your group delay suffers again. There are many, many other approximations, either polynomial approximations or simple other approximations that you can use, but we're going to basically base most of our design in this course on those 3. And then we'll extend them for other things.